I'll admit it. Building the combustion chamber for my RC turbine project was probably the part that intimidated me the most. It combines ultra-thin stainless steel components, several critical welding operations, and very little margin for error. In this video, I'll manufacture the complete combustion chamber from scratch, test a low-cost cold TIG welder, compare it with traditional spot welding, and share my conclusions after using both methods. Hi guys, I'm Alfonso, and welcome to the channel. Today we're continuing the RC turbine project. If you're into CNC machining, TIG welding, DIY engineering, and turbine building, you're in the right place. The combustion chamber is one of the most complex assemblies in the turbine. The outer and inner liners are made from 0.3 mm stainless steel sheet, while the front and rear end caps use 0.4 mm stainless steel. The design also includes 12 vaporizer tubes, a removable fuel manifold, and several brazed and welded joints. Working with material this thin is challenging enough. The real question is how to join everything together without distortion or burn-through. Before any welding can begin, the combustion chamber components need to be manufactured. The inner and outer liners are machined from 0.3 mm stainless steel sheet. Machining material this thin can be surprisingly difficult, so I use the double-sided tape and cyanoacrylate method to secure the sheet to the CNC table. Once machining is complete, the part can be released easily using a thin scraper. The longitudinal seam uses a small Z overlap that I form using a simple custom-made tool. This provides accurate alignment and improves the rigidity of the assembly. The liners are then rolled into their cylindrical shape using a sheet metal roller. At only 0.3 mm thick, the forming operation is straightforward and produces very good results. The front and rear end caps are made from 0.4 mm stainless steel. Their profiles are CNC machined using the same tape fixturing technique. To produce the final shape, I use a simple metal spinning setup on the lathe. A custom fixture supports the workpiece, while a bearing progressively bends the flange into shape. Although the process works reasonably well, achieving perfectly repeatable results proves more difficult than expected. Sometimes the parts come out exactly as planned, but occasionally wrinkles appear at the edge and the part becomes unusable. Another challenge is controlling the final dimensions, because the flange rarely ends up at exactly 90 degrees. After several attempts, I decide to change my approach. Instead of forming the end caps from sheet metal, I machine them directly from solid stainless steel stock. Recently, I purchased a low-cost TIG welder that includes a cold TIG mode, and this project seemed like the perfect opportunity to test it. One important warning: don't make the same mistake I did. The wiring diagram shown in the manual is actually incorrect. The written instructions are correct, but unfortunately, they are only available in Polish. After correcting the polarity, the machine performed much better. The welder allows pulse durations as low as 30 milliseconds and currents down to only 10 amps. For my first experiment, I weld together two utility knife blades using 30 milliseconds and 80 amps. The result is surprisingly good and gives me confidence to continue. I then move on to the outer liner, using 30 milliseconds and approximately 60 amps. The inner liner and front end cap are welded using the same technique. So far, the results are very encouraging. The flame tube requires a series of formed craters around the air holes. To perform this operation, I manufacture a set of simple custom tools. The process is straightforward and produces very consistent results. The finished flame tube looks exactly as intended. Now it's time to complete the rear end cap. I initially continue using the metal spinning process. But after several attempts, the limitations become obvious. Some parts are acceptable, while others develop folds and wrinkles that immediately ruin the component. Because of these inconsistencies, I eventually switched to fully machined end caps. The new parts are machined from solid stainless steel and provide much better dimensional control. The finished caps are robust, accurate, and considerably easier to assemble. Next, I cold TIG weld several M3 nuts onto the rear end cap. These nuts will support the removable fuel manifold. The vaporizer tubes are also attached using cold TIG welding. To guarantee accurate positioning, I manufacture a simple alignment fixture. This keeps all 12 tubes perfectly located during assembly. The final result is clean, precise, and mechanically strong. For the fuel manifold, I switched to silver brazing using 60% silver filler rod and an oxy-fuel torch. To maintain alignment during brazing, I insert a steel rod inside the 3mm brass tube. Before bending the manifold, I anneal the brass tubing at approximately 400 to 600 degrees Celsius. This softens the material and greatly reduces the risk of cracking. Once the manifold is complete, I perform a gas flow test. All 12 outlets produce very similar flames, indicating good flow distribution throughout the system. At this point, I also want to evaluate spot welding as an alternative joining method. Since I don't own a spot welder, I decide to build one. There are countless designs online based on modified microwave oven transformers. I follow the same general concept, but design my own machine around a 3D printed frame and gun. Construction is straightforward and uses inexpensive components. On the very first test, the machine successfully joins two pieces of 0.3mm stainless steel sheet. The thicker machined front cap requires a slightly longer weld duration because the flange is approximately 1 millimeter thick. The outer liner, however, requires only a very brief pulse. The welding duration is controlled manually using the foot pedal. I continue joining the remaining components until the complete chamber is assembled. The weld quality is consistent, and the process proves to be surprisingly effective. With all components completed, I can finally perform the final assembly. Everything fits correctly, including the interface with the nozzle guide vane assembly. The combustion chamber is now complete. So, which process would I choose? Both cold TIG welding and spot welding are perfectly capable of building a combustion chamber like this. However, if I had to choose only one method, I would probably choose cold TIG. Spot welding is fast and highly effective for sheet metal assemblies, but cold TIG offers much greater versatility throughout the turbine project. It can be used on a wider variety of components and joint geometries. I still have a lot to learn about the limits of cold TIG welding, but even this inexpensive machine exceeded my expectations. The combustion chamber is now finished, and we're one step closer to seeing this turbine run for the first time. If you'd like to follow the rest of the build, consider subscribing. Thanks for watching, and I'll see you in the next one.